Gang, what is the wattage of this resistor? What say you? Let's pop this out to M. Any idea what the wattage of that baby is?
12.
Oh, did Jazzy say that?
No, the other M.
Oh, that M. What did you say, M?
I don't know.
Okay, not really sure. Can the other M do it? What the wattage of that equivalent resistance is? St. Nicholas, can you help around?
24.
Hey, 24. So again, getting 12 joules per coulomb times, again, 2 coulombs per second. So 12 times 2, 24 joules per second, 24 watts. So the whole circuit is doing 24 joules of work every single second. And making, these are all light bulbs and making light energy against a 24 watt circuit. Okay, again, last idea that I think I'm going to cover here with you, and then it's just all little things, and that's the resistance of a wire. Okay, so wire really does have resistance. Okay, when we do circuit problems, we do ignore the resistance of the wire. We say they're ideal wires. That's like eliminating friction in mechanics. Again, we're eliminating electrical friction. Again, here's what the resistance of a wire depends upon. And again, they like to just ask relationship questions with this equation. So there it is, gang, R, the resistance of a wire. It depends upon 3 things. Really, it depends upon 4 things, but we're only going to take into consideration these 3. Again, this Greek letter rho. Again, that represents, that takes into consideration, again, the type of material that the wire is made of. Again, we call it the resistivity of the wire. So this Greek letter rho represents the resistivity. Again, that depends upon the material that you have. Again, that's something you just look up in a textbook. Again, I'm going to show you in a second, gang, a chart that comes right out of a textbook that lists the resistivities of different wires. So, for example, gang, is it gold? Is it copper? Is it aluminum? Different types of wire are better conductors than others. Again, not everything is identical in conducting electricity. Again, some materials offer more resistance to the flow of charge than other materials. So again, that's what this Greek letter rho takes into consideration. Hey, what the material is made of. So copper won't have the same conductivity as aluminum or gold or silver or iron. Again, the L. Again, that just represents the length of the wire. Gang, in the past, I would always tell kids not to really memorize this equation. Now, gang, I think you get to use the formula sheet on both parts of the test. Gang, this is on the formula sheet for you. Gang, I would have the kids memorize it from a kind of common sense point of view, and then I would say, okay, right before the exam, look at this equation. Oh, yeah, that makes sense. Gang, doesn't it make sense that if I have some wire that goes from here to here, again, there's a certain amount of resistance in that wire. But again, if I take this light bulb, again, I put it in the middle of the football field. Again, I take and run a wire from here all the way to the middle of the football field, connect it up to this end of the wire. And then I take a wire from this end of the light bulb and run it all the way back up to here to the battery. Again, doesn't that make sense? More resistance there to the flow of charge, the longer the wire. Okay, or here's another way of thinking about it, gang, the traffic analogy. Again, you're going down a 3-lane highway. All of a sudden, it narrows into 1 lane. And it does it for just 2 blocks. Again, there's going to be resistance there. Trying to squeeze everybody into 1 lane. But again, it opens back up into 3 lanes again relatively quickly. Again, now narrow that down to 1 lane for 10 miles. Again, the longer it is, the more resistance. So again, the greater amount of wire you have, the more resistance you're going to have. And then gang, down here, the A, that represents the cross-sectional area of the wire. Again, the larger the cross-sectional area, the less resistance you have. Again, I like to think of it as, again, traffic flow too. You have a 1-lane highway. All of a sudden opens up into 3 lanes. You're going to have less resistance there to the flow of traffic. So again, I have all kinds of different wires up here, all different thicknesses. Again, this is the standard kind of wire that you run in your home. Again, it's called 15 gauge wire. And it can handle take that back. This can handle 15 amps, and that's it. And it has a certain thickness to it. It's the easiest to work with because it's the thinnest. Then there's another type, gang. It goes up, and this one can handle 20 amps. It's really a little thicker. You can't really tell by looking, but if you bend, you can tell. And then, gang, I have some really much thicker wires here that really you would use for maybe sending, powering up your stove or for really high current applications. So, again, the thicker the wire, hey, the more current it can handle. The thinner the wire, the less current it can kind of handle. So again, that formula, they like to ask a lot of relationship questions with it. So for example, I think I have a relationship question right here using this equation. As a matter of fact, gang, here's the table, gang, of different resistivities. So gang, notice something like rubber and glass. Gang, we know those things are good insulators. They don't conduct well at all. And sure enough, gang, look at their resistivity. Gang, let's make it a 50. 50 times 10 to the 13th. Glass, gang, depending on the type of glass, gang, anywhere from 1 to 10,000 times 10 to the 9th. Gang, huge resistivities. Gang, resistivities in the numerator, so the bigger the number, the more resistance it offers for resistivity. Gang, look down here at copper. Gang, 1.68 times 10 to the minus 8th. Gang, up here 10 to the 13th, minus 8th. Again, resistivity much lower, so much less resistance in copper. Again, what's a better conductor of the electricity? Again, copper or silver? Copper 1.68 times 10 to the minus 8th, silver 1.59 times 10 to the minus 8th. Again, which one of those materials would be the better conductor of electricity? Any idea what pops up to Matthew? Again, silver would be. So some people say, well, why don't we use silver for all of our electrical wiring needs? Ooh, too expensive. Muy bien. Nicholas knew right away, huh? Again, this one surprised me. I would have thought gold was a better conductor than copper, but it's not. It has a higher resistivity. Again, aluminum. Again, they do use aluminum. It offers more resistance, though, than copper does. Okay, here we go. Again, typical. Gang, relationship kind of question. Gang, if the resistance of wire 2, gang, here's wire 2. Is the resistance of wire 2, here, wire 2, gang, the same as that of wire 1, here's wire 1 up here. Gang, twice that of wire 1, or half that of wire 1. So gang, I'd like to just take each idea at a time, so again, here's my equation that gives me the resistance of any wire. And again, it's the same kind of wire, gang, so rho is the same for both, so we don't have to take that into consideration. That's not changing. So I'm going to say this, gang, there's a wire 1. I'm going to say it has a resistance R. I don't know what it is. It doesn't matter. It could be a hundredth of an ohm, a thousandth of an ohm, a millionth of an ohm. It doesn't matter. But gang, wire 2. Let's take a look at L. Gang, what happened to L? This has a length L, that has a length 2L. Again, did L get bigger or smaller? Let's pop this out to name. Bigger. Yeah, it got bigger. Again, how many times bigger did it get? Let's pop this out to Gus. Hey, it's 2 times bigger. Again, if it got 2 times bigger, again, what kind of relationship exists between R, the resistance of the wire, and the length of the wire? Let's pop this out to Jazzy. Hey, what's the relationship between the resistance of the wire and the length of the wire? Yeah, they're directly proportional to one another. So again, if we double the length, guess what that's going to do to the resistance? What do you be saying? Let's pop up to Kabir. Yeah, it's going to double it. So again, I put a 2 out in front of the R, because that doubles it. Okay, now this one's kind of tricky, gang. The other thing then we have to take into consideration is the cross-sectional area. Again, last year I used to have fluids in before this, and fluids travel through a pipe, and we would have the same kind of questions for fluids. Gang, the diameter looks like it doubled. Gang, does that mean the area doubled? What say you? Let's pop this out to Gus. No. Gang, as a matter of fact, gang, what happens to the diameter? When we say the diameter doubled, hey, the radius doubled also. But gang, it looks like the cross-sectional area of a wire is the area of a guess what? Begins with a CI. What do you be thinking? Let's pop this out to L.
Circle.
Yeah, it's the area of a circle, huh? And again, this is on your constant sheet for you. You don't have to memorize it. It's pi r squared. So again, what this says is this, and this. So again, a lot of kids be saying, "Ooh, the radius got twice as big, so the area doubled." No, it didn't. Again, the relationship between the area of a circle and the radius is the area is directly proportional to the square of the radius. Again, whatever you do to the radius, you have to square it, and that's what happens to the area. So again, when we doubled the diameter, we really doubled the radius too. Again, if we double the radius, well, 2 times 2 is 4. Again, the area went up by a factor of 4. Again, there's 4 times more area right there than there, believe it or not. A lot of kids want to say, oh, that's twice the area. No, it's not, because it's twice the radius. Again, the area goes as the square of the radius. So when you double the radius, you quadruple the area. Triple the radius, well, 3 times 3 is 9, 9 times the area. Again, 4 times the radius, 4 times bigger, quadruple it. Again, you're going to get 16 times the area. Okay, so it looks like the right answer is which one? Let's pop this out to sturdy.
C.
Gang C, huh? But womp. Okay, go ahead and try this one, gang, on your own. I'm not gonna. It's just a plug and chug using that equation. I think I had. Did I have the resistivity of copper for you? That page on your notes. So you're gonna have to look up the resistivity of copper, multiply it by the length of the wire divided by the cross-sectional area, and you should get this. Okay, again, just kind of going over what the resistance of a wire depends upon. The longer the length, hey, the greater the resistance. The greater the cross-sectional area, the less the resistance. And what the material is made of, that's the resistivity. And again, the greater the temperature, the more resistance to it. We're not going to take that into consideration. As a matter of fact, gang, if you look at that equation sheet that they lead you to use on the test, gang, under the section dealing with electricity, again, we've covered all these equations now. So again, this first one up here, you recognize that? What's that? This first equation. What do you be thinking? Let's throw this out to Zach.
I use space now.
Okay, that's Coulomb's law. Again, the electric force equal to, again, K, Coulomb's constant, Q1, Q2. This is the electrical equivalent of Newton's universal law of gravitation. Hey, what's this? Anybody know what that is? That equation. Any idea, Gus?
That is the current.
Yeah, current. Current is numerically equivalent to the rate at which charge is flowing. How quickly, how slowly charge flows through a wire, huh? Again, so this is the new one. This is the one I just threw at you. Hey, the resistance of any wire is numerically equivalent to, again, the resistivity of the wire, the length of the wire, cross-sectional area. Hey, what's this? Any idea, Mitch?
Not sure.
Okay, not really sure. In other words, they write it a little differently than me. Any idea? Let's pop this out to Z squared, what this one is.
Ohm's law?
Yeah, that's Ohm's law. Again, current is numerically equivalent to the, again, difference in electrical elevation. So they have the change, there's a change in a difference in electrical elevation across an electrical device. Take that electrical pressure divided by the resistance and you get the current. Again, gang, this is power, current times the voltage, current times voltage power. This is the resistance of resistors in series, just add them all together to find out the net resistance. And this is the resistance of resistors, the net resistance of resistors in parallel. The 1 over the net resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So really, gang, these are all we've covered all those equations now that are on that equation sheet. Okay, this is, again, a lot of people will typically ask me this question right here. I want to run this circuit. How many light bulbs can I have on that circuit? So again, the power and voltage on the light bulb read. Again, 60 watts, 120 volts. Again, in your home, all light bulbs are put across 120 volts. Again, as a matter of fact, all outlets in your home. Again, when you take your metal or your outlet, again, and plug it into this outlet here, again, the metal that's on that plug connects metal in the outlet. Gang,